Welcome to the Windshield Chronicles, a mental sequence of operation. The ESCO Institute is dedicated to bringing you quality HVACR training products and resources. Learn more at escogroup.org. All right, so this is going to be a interesting conversation. This is one of those, I always like to talk about, well, how far are we going down into the conversation? Well, we're going to start at an overview, like 1,000 foot, and then we're going to dive really deep into flame rectification and understand a little bit about what that is. So joining me today is author of our gas heating book, Jason Obrzut. How are you?
Thank you, Clifton. I'm doing pretty well. How are you?
I got to be more professional. Every time I have you on here, it's like, oh man, it's my buddy Jason, and I call him buddy. But it's so much fun when we get together, and because you and I see things from such a similar perspective, and we always have a good time diving into these topics. And I have to say, for me personally, this was the topic that when I first started teaching, I really didn't understand. I thought I had a decent idea, but I didn't know what that entire rectification looked like. And so I got into diving a little deeper into it, and you cover it really well in our gas heat book. I want to make sure everyone that's joining us, if you don't know what we're talking about, we have a really, really good instructor array of education on gas heating. So the book, the e-learning, we've got the entire digital copy of it. So the entire curriculum for teaching gas heat in our classrooms. And so let's talk about rectification a little bit. And I think to do that properly, we need to be able to go back and talk a little bit about how we got into flame rectification.
I had a good understanding of this, but when I started teaching, what I understood and didn't communicate to the students the way I understood it. No. So what you're going to show today, things like this are definitely beneficial. I could say, listen, this is how it happens.
Yeah.
And they would all look at me like I had snakes coming out of my head. They're like, wait, say that again?
Wait. Hold on. Back up. What do you mean? So
just because you understand it doesn't mean the others will.
Exactly. And so when we're teaching this in class, it's very important to know how to teach rectification, because it's really... It's for me, it wasn't exactly what I was expecting it to look like. So let's do a little history here so we understand the difference between voltage generation and flame rectification, right? And when we talk about our earlier furnaces, now I grew up working on thermocouple driven furnaces. Almost everything that I worked on had a thermocouple on it. So whether it was a gas fireplace, whether it was a gas furnace, whether it was a water heater, it all goes way back into the early 1800s when Thomas Johann Seebeck found this really interesting effect. When he applied heat to dissimilar metals, it created a magnetic field, right? And so when we start talking about electrically, well, magnetic field can turn into current when we utilize it properly. So we started experimenting with thermoelectric current as early as 1821. Well, what does that mean to us? Well, that's actually the technology that we put into play into thermocouples. And there are still thermocouple driven devices out there. But the difference between thermocouple and flame rectification is very different. So if you learn from someone who understands thermocouples and you move to flame rectification, you may not have gotten the full clarification. All right, so let's talk about this, right? Thermocouple. Two dissimilar metals fused together at one end. When the thermocouple is heated, it generates an actual DC voltage. We create voltage with a thermocouple, right? So we have the difference in temperatures, we have the magnetic displacement, and so we actually generate DC voltage directly off from our thermocouple. So the more heat, the more voltage. And we have different types of thermocouples. Basically, depending on the construction of it, we can get different voltage ratings, right? So we're talking about millivolts, very, very small amounts of voltage. So if we think about like a C-type thermocouple, we know that at a certain heat range, we're going to get a certain voltage. So like on that C-type thermocouple, if we are at around 3,000 degrees Fahrenheit, we're going to generate around 30 millivolts DC voltage. So a common thermocouple is going to be in that range, 18 to 30 volts DC, millivolts DC, right?
And this is voltage being generated right out of nothing from metals being heated. Nothing is supplying anything to this other than the flame.
Exactly. And we are going to do work with this. When we talk about K-type thermocouples, like for our meters, well, same kind of thing. We're generating a voltage that our meter is going to read and interpret it as temperature. Well, that's all fine and dandy when we're talking about thermocouples. And if maybe we need a little bit more, because remember, we're going to do work with this. So on a residential light commercial gas furnace with a water heater with a fireplace, we're going to generate some voltage and we're actually going to do work with that voltage. Well, what if we need more? What if our valve is larger and we're talking about a commercial gas valve or an industrial gas valve that's got a bigger diaphragm and a bigger solenoid and we need more power? Well, we just take thermocouples and we put them into series and we create more voltage. That's all it is. So we're applying heat onto multiple thermocouples so that we get a common higher output voltage. Works great when we're talking about a larger gas valve, right? So if we're typically working on a thermocouple, we can actually measure the voltage that's being output from that. And Jason covers this completely in our gas heating book. You can measure the voltage to see how good your thermocouple is working. A lot of time in the past, we just cleaned them. If it held, good. If it didn't, we replaced it. Well, you can actually measure that. And so we can measure the voltage on a thermocouple as long as we have proper heat applied to that top half inch of the thermocouple, somewhere 10, 15, 30 millivolts DC. If we're talking about a thermal pile, well, now we are just generating more. So it depends on the size of the thermal pile, but typically in that, 540, 750. So 500, 600, 700 millivolts is pretty common.
So what this can do, it can tell you not just about your thermocouple, your thermal pile, but actually the quality of the flame being used to heat it.
Yeah.
If you have a brand new thermal pile or thermocouple and you're getting these low readings, it may be the issue is the quality of that pilot flame. It might be a weak flame. It might be dirty. Right. So there's a lot of things you can do with it.
That's super important on this conversation. So what we're saying is that with a thermocouple and a thermal pile, heat is absolutely crucial to be able to use this safety device. Right? The heat is the function of generation for voltage. That's what I was taught. Well, that was great until we moved into newer technology in the 80s and 90s with solid states. So let's talk just for a second so we understand completely what we're doing. So if we have say that we've got a pilot-driven gas valve. So we're going to push down on our pilot button. We're going to supply fuel onto that pilot tube. We're going to light that with whatever device, whether it's a hand ignition, whether it's a direct spark, whatever that is. We're going to create a hot enough flame, hopefully 2,000, 3,000 degrees. We're going to get hot enough that we're going to generate voltage off from those dissimilar metals. And that voltage is going to be applied to a magnetic coil. And so we have an electromagnetic plunger, a plunger inside of electromagnetic field that's going to hold that plunger down, right? We generate enough voltage. We have enough magnetic field. It's going to draw it in. Okay. So that's how those work. So we're heating up our thermocouple to generate voltage. And that's how all thermocouples and all thermal piles work. Here's the thing that we're not always instructed on. When we moved from thermocouple systems with manual ignition controls and we moved into electronic ignition, that almost all went away. And we moved into the era of flame rectification that doesn't rely on heat at all. And this
so it should
is
be pointed out that the thermocouple itself was a safety. All right. So if the pilot went out, the thermocouple or thermopile would stop generating voltage and the valve wouldn't be able to open to let the gas out because there would be nothing on the other end of that valve to ignite that gas that we were letting out. So it was more like a safety device. And that function, if you will, the safety portion of it carried over to the flame rectification, but the principles did not. It's a completely different principle.
Exactly. And that's where I got hung up the most because I was not explained this. And so once I learned it, then it's like, okay, how do I teach that? Well, like everything else, it comes down to understanding what's going on. And we're going to dive into this. And if you hang around, we're actually going to maybe even potentially construct one so we can show you what it looks like electrically. Okay. Let's clear our mind for a little bit and let's think about what's happening here so that you can completely get a new perspective if you don't understand it the way that we're going to show you. So with rectification, we absolutely are not relying on heat, right? So there's a misconception that we need to break real quick. So with flame rectification, we are actually completing an electrical circuit, right? So we are actually going to apply voltage onto a flame rod. We're going to pass through the flame. We're going to go through this process of rectification, and we'll help you understand why it gets that name, what it's actually doing. And then we're going to return back on our ground. And so we have to stop for a minute and go, well, wait a minute. Maybe I wasn't explained that that's what happens with this flame sensor. And by the way, you'll see it called a flame sensor. It's really not. It's a rod. I'm going to show you what it's made of here in just a minute.
It's just a conductor, right?
That's it. That's all we're doing. It's a means of applying voltage into the path of the flame. All right. So let's think about this, because we're going to come back to this here in a few minutes, and it's really going to sink in. So what we're actually doing, we are completing a circuit. We're applying voltage onto the rod or probe or sensor. You'll see different names. It's just a rod. We are applying voltage, AC voltage, onto that rod. It's passing through the flame. And because of the ionization, the combustion that's happening in that flame, we're actually going to put a load on the flame as it's making its way back to ground. And so we are creating an electrical loop through the fire. Now,
flame does conduct electricity. It's not a good conductor, but flame will conduct electricity.
Absolutely, it does. The ground is one of the most important pieces of our circuit, and we'll show you here in just a second. So let's think about this electrically, right? Just so we can see what's going to happen. If we think about this electrically, that means we're applying an AC voltage. We are going to convert into a DC looking signal only because that's what happens in the ionization side. And so our meters can't read it as AC anymore. It's not a clear path to ground. Remember, we're jumping through flame. We're jumping across carbon molecules and carbon atoms, actually, carbon atoms and water molecules. And we're going through this effective ionization that's in the flame. We don't have a straight path to ground. So our meter can't read AC. It reads it as DC. And we're putting a load on that flame, which is why we are reading in amps. So we're putting a very, very small amount of voltage through it, and we're putting a very, very small load on that flame. So we're reading it in microamps, and we're reading it in a DC voltage. Okay.
It is basically half of the sine wave, because the flame does have a very high resistance. The circuit board is usually only seeing about half that sine wave, and on your meter, you're only going to see about half that sine wave, which is why it shows up in DC and not AC, right?
Exactly. But it is 100% AC voltage. I'll even show you on a wiring diagram. A lot of people have missed this. When you read your wiring diagram, it'll completely make sense. And we'll actually show one for this particular model that I have right here. So let's think about this now. If we approach it from an electrical perspective and we start using our electrical trained brain instead of our heat trained brain, this entire process will just make sense like a light bulb. So if we take a burner assembly, we are going to, first thing we're going to do, we're going to apply an ignition source. So whether it's direct spark or it's hot surface ignition, we're going to apply the means for igniting our fuel, our A3 highly flammable fuel, right? Once we introduce fuel into our circuit, our igniter is going to ignite the gases coming out of our burner because it is mixed with fuel. It's been diluted to an area between its lower flammability limit and its higher flammability limit, right? We're making combustion. It's going to pass across our burner assembly, and it's going to light the rest of the burners. So we have a complete path of flame. Very important to verify that all of our burners are lit. And this is where our circuit comes into play. At the opposite end, we now have a dedicated wire going from the Molex connector of our furnace board right over to the flame rod. And I will always call it a rod because it's just a rod, right? And it's typically orange. So we're going to have a dedicated wire directly from the control board to the flame rod. Here's another thing that a lot of people miss. A lot of people don't recognize that we actually have not just a ground, but we have a dedicated ground going directly from the Molex connector of our board straight to the burner box. And it is landed there by the manufacturer for this particular reason, because it is part of our complete circuit. The ground is as important as the rod itself, as well as the surface of those burner faces. Because remember, we are applying AC voltage. And a lot of people are going, oh, that's crazy. We don't apply AC voltage. Well, let me show you. So let's take a look at the wiring diagram for this particular 80% Goodman furnace. If we look on here, this is where people we just skip it. It wasn't until I looked at the wiring diagram myself and I went, oh my gosh, it was right there in front of me the whole time. If we look at this wiring diagram, my flame sensor, the manufacturer is actually calling it a flame sensor. I'm going to call it a rod because it's not sensing anything. It's just a rod made of Canthal. But if you look, it is on the high side of our transformer. It is on the same side of our transformer as our hot surface igniter, our induced draft blower, and our circulating blower. The only difference is our voltage has been reduced to typically a lower, safer voltage rating for handling. But it's actually AC voltage. So in a classroom, here's the way that we want to show that. Or even if you're a technician and you want to verify it yourself, next time you're sitting in front of a gas furnace, here's what you do. So let's walk over to a meter. Let's put our meter on volts AC. My thermostat is not calling for heat, but I have power applied to my furnace, which means everything on my high side has the potential for voltage right now. So if I go from ground and I go directly over to my flame rod, I am actually producing right now 43.4 volts AC directly onto my sensor, my rod. Okay. So that's step one, to be able to see what we're doing. So we're going to apply AC voltage back onto that wiring diagram. Let's go over that wiring diagram and let's complete this path. So what we're going to do on that flame rod, we apply AC voltage. That AC voltage comes out of our board and it's going to go to the rod. It's going to pass through the flame back onto that dedicated ground wire. And it is such a dedicated ground wire that if we look at this separate burner assembly that I have here, Jason, this is something that we can never overlook on a gas furnace, right? Our dedicated ground wire from that control board lands on the burner box so that we can get as close of a connection to our burners as possible. It is such an important wire that this particular one actually is a straight wire from here all the way back to the control board and is a component of the wiring harness of the furnace. It's not a separate wire. It cannot be relocated. It is there as a dedicated path. And so what we're going to do, we're going to talk about measuring this. What do you think, Jason?
I think that's a great idea. Another thing to point out is just because that wire is present, if the furnace itself is not grounded upon installation, then we may have some, that's where the question comes up. Well, you got to have a really good ground.
Yes.
Well, you may have to, depending on where the furnace is located and how you're running the electric to it. If they're using Romex and flexible gas line, then you may not have a reliable ground. You may have to run a wire from, and typically there's a stake on that gas valve somewhere where you can stake a wire on and run it to a water pipe or a gas pipe or something of that nature. But that's where you run into some ground issues. From the manufacturer, they've got a good connection there. They've got a solid wire, no breaks. But after installation, you may not, depending on the way it was installed and the materials that were used to install it, we may not have the best ground after installation, and we may throw some intermittent flame sensor problems.
Exactly. So what we're doing when we're teaching we're teaching our students to measure the flame current, that's really what we're doing. We're validating, are we making it back to ground? That's all that we're actually doing. So let's talk about this for a minute. If you've not been explained this, I'm going to very quickly just demonstrate what we're going to do, but we're going to show you, we're going to prove to you that it's actually electrical. So like if we are measuring the actual microamps that's passing through there, if we're measuring the load that is on that flame, what would we do? If we're measuring any kind of a load, right? We're going to put our meter in series with our load. So what we're going to do, we're going to disconnect our, like I said, it's typically orange. We're going to disconnect it. We're going to put our meter in series now, right? So literally just disconnecting the wire, putting our meter in. So all we've done is we've completed that loop. So if we go back to that wiring diagram, we'll actually see exactly what I just did. So I took the orange wire off from the flame rod. I put my meter in series so that my meter is measuring the current that is passing through, right? So if we're reading amps of any kind, we're reading the current. And that's actually what we're going to do. Now, here's the important thing. Manufacturers of control boards, electronic ignition control boards, set a range, an acceptable range for that microamp. It's typically around 1 microamp DC. So if we get less than that, the board has the potential for locking out. So this is why it's critical for us to measure what those microamps, just like Jason said, what if it's a flame that is just, if our gas pressure is low and our burners are dirty, we may not be getting the proper current passing through. So we can actually measure it to see what we have.
I want to point something out real quick, Cliff.
Yes.
That when your meter is in that position, it allows voltage to pass through it.
Right.
Okay. So if you accidentally touch ground with either end of that, you're going to have some fireworks. So you have to be like, you have the insulated clips on your alligator clips there. Right. Don't let the meter lead touch the burner, touch the furnace.
Sure.
It's got to be firmly connected to the wire and to the flame sensor, and nowhere can we introduce the ground or we're going to have some problems.
So Jason, let's do a quick mental sequence of operation. If I'm a gas-fired furnace, what's my sequence?
So number one, if I'm a circuit board, I'm sitting waiting for something to happen. And that something is the thermostat asking me for heat. So the first thing I need is for the thermostat to ask for heat.
All right, we'll go do that one. Now I'll have a little bit of background noise as the blower and stuff kicks on, but I'm going to try to keep close to the microphone.
I'll try and keep up with the speed of the board there.
Yeah.
As a board, once I receive this input signal from the thermostat, my reaction as a board is I'm going to send an output signal to the inducer motor. All right.
Sounds
the combustion blower, power venter, whatever they want to call it. It has a million names.
There goes one.
There goes. And the purpose for that blower is to induce into the heat exchangers, the combustion air and the gases. Mm-hmm. But we also have a safety switch in there that needs to make sure that our flue is clear. We have the proper airflow through the heat exchangers, and that's that safety, that pressure switch. So when that inducer comes on, the pressure switch is going to close. And as the board, I'm going to get a signal from that pressure switch to say, hey, everything's a go, move on to the next step. So when the board gets that signal in from the pressure switch, it's going to react by putting a signal out to the igniter. The igniter is going to have a warm-up period, 30, 60 seconds, whatever it happens to be. And after that timer, it's then going to send 24 volts to the gas valve, which is going to let the gas out, hits the igniter, and we get ignition. Once we get ignition across all those burners, that flame sensor, rod, whatever we want to call it, there's going to be a path through there to let the board know, hey, we got ignition. We've got current through here. Once it sees that current, it's going to allow 30, 60, 90, 120 seconds, and it's going to turn on the blower motor. So all it is a series of inputs and outputs in a very specific order.
That's it. So what we just did was in that sequence of operation, after the igniter comes on, after the gas valve comes on, we have a very short window of time.
Usually
that we
4
have
seconds. Yeah,
that's right. That we have to prove that there is actually flame there, but we're doing it electrically. So what we did was we created our little flame rectification circuit using a 10 mega ohm resistor in a parallel circuit along with a 2.2 mega ohm with a 404 diode in series. When we did that, we created a microamp load across from ground to the flame rod. And so you'll actually see we are running right now, and my board is as happy as can be. It timed on, brought the flame on, and I'm actually measuring about 1.9 microamps DC. It has 1.9 microamps DC current passing through the flame, creating the electrical circuit that we know as rectification. And that's really it. It's kind of complicated,
a good way
but
to
when you think
explain
about
this, when you start, if we start at that 30,000 foot level and say, listen, it's kind of like a switch that closes.
That's it.
All right. All you're doing is closing a circuit. That flame hits the rod, closes the circuit, and allows current to flow. In the absence of the flame, the circuit is open, no current flows, and we get no ignition, or we get no sequence. So when you're trying to explain this to somebody, students or colleagues or coworkers, say, listen, it's kind of like a switch. It's open or closed. That flame closes the circuit, and absence of flame opens the circuit. And then you can take the deeper dive and say, well, actually, here's the current, here's how it's going. The flame conducts electricity to the ground, that sort of thing. But when I started teaching it, I started using the switch thing, and the students started getting that.
Yes. Yeah, we're adding it into the electrical circuit. We are taking an electrical circuit and adding it into the rest of the electrical circuits. That's all we're doing.
And
Nothing
it's
to
a
do with
very
heat.
small current, again, because the flame is not a great conductor. It does have high resistance.
Yes.
So it's a very small current going through there. We got to put our meter in series with it to see that current in DC microamps.
Exactly. We'll see you all in a couple weeks on Did You Know? The ESCO HVAC show.